Let's talk about common applications of the derivative. Previously, when we were trying to define the idea of limits and see the interactions that we're going to have with the notion of the derivative, we talk about the average and instantaneous velocity. The average velocity was given by the change between a point and moving a little bit from that point and checking what was the difference between the images over the difference in the space that you're moving. Now we can, if we consider the function in terms of time, then the space that something is moving is going to be an interval of time. And in particular, then we can talk about that generating both the average velocity, and then later when we take the limit, making that interval of time small, then the instantaneous velocity. One example of this will be apply that to position and velocity of, let's say, a patrol car. A police station is located along a straight eastway freeway at noon, so we call noon t equals 0, and a patrol car leaves the station heading east. The position of the car is given by the function s equals f of t and gives the location of the car in miles east if s is bigger than 0 or west if s is less than 0. Now you can see the graph here of the function f of t. So we got now this is the variable s, which is the position, and this is the time, hours, afternoon. So as you can see, for the most part, from the interval of time from 0 to around almost 3:15, we have that the function overall is positive and is being working towards the east. But now, after 3:15, you can see that is going now to the west. So the point where it gets back to 0, it can also be meaningful here because it means that it went backwards to the station. Now the graph of the position indicates that the car is traveling at 80 miles per hour between t equals 0 and t equals 1.5. You can see that in here. And you can take these points to calculate what is the average velocity between this point and this point. And that's how you're going to get that information. Now, the car is a rest position and it did not change speed from t equals 1.5 to t equals 2. So this is the interval where it's constant. You notice that the derivative is here. The derivative of the position is 0. It's flat in here in this position, constant. So there is no change on the velocity, and the car is at rest. Finally, starting t equals 2, the car distance from the station decreases. So you notice that this signal the return to the car to the station, and eventually is going to end up 20 miles west of the station at 3.5, which is like 3:30. Okay. So as you can see, we can pretty much track, given the function of the position, we can track things like the speed using the average formula, and we can also describe position in one direction or the other. Now, the position of the car at 3:30 is minus 20, and that negative sign indicates that the car is 20 miles west of the station, and the position of the car at 2 p.m. was 80. Okay, so we can calculate the displacement between these two moments over here, and we can calculate the delta of the position, which is f of 3.5 minus f of 2, and that's going to be minus 20 miles, and here minus the positive 80 here, and that's going to give me minus 100 miles. Now the average velocity the average velocity now is going to be the difference between this difference between the difference in the time. So I take 3.5 minus 2, and that's going to give me 1.5 hours. And so the average velocity is going to be given by minus 66.7 miles per hour. So this is giving me how much the average velocity is moving between this time. Of course, that's not the instantaneous velocity, which will be a better approximation. Now, in general, you can talk about velocity and speed and acceleration when you have any function that is describing movement. So if you have that s equals f of t is a function of movement, the speed is the derivative of that function, and it can be considered the velocity. The speed really is the absolute value of that, because this velocity can be negative depending on the direction that you're going. And but the speed is the absolute value of that, and it's just going to tell you how fast it goes. Now you can also take the derivative of the speed. This is the rate of change of the speed with respect of time, and of course that means how fast are you changing the speed. So that means the acceleration at a certain time. So if your function is giving you the position, the second derivative is going to give you the acceleration of the movement. Okay, and this is going to work out regardless of your setup. So some examples here is I have the function of position being t squared minus 5t. This is the position of certain particle. Now, if I take the derivative, then that's going to be 2t minus 5, and that just shows how the velocity is moving as a line. You can see from here, if you take the slopes of the tangent line, these slopes are being negative, in here transition to 0 between 2 and 3, which is this point, and then it starts to transition to positive here, which you see reflected here. Now, if you think about acceleration, we take the derivative of this, and you can see that we get 2. So we're actually going to have a constant acceleration. And you can see that from here as well, because the velocity is increasing constantly in a line. It is always increasing in the same way, the speed. And so that means that there's no change in the acceleration. Now let's look at a more particular example. Suppose a stone is thrown vertically upward with an initial velocity of 64 feet from a bridge 96 feet above a river. If we use Newton's law of motion, the position of the stone, that is measured as the height above the river, after t second is. And so first we get the function s equals minus 16t squared plus 64t plus 96. Notice that the initial position is going to be marked here as 96 feet. And because we have a parabola or a quadratic equation, we actually can observe what is the maximum of this movement. Okay, so we find the vertex of this, we obtain the maximum value that we can get for the position. Now, taking the derivative of this, we can find out what was the initial velocity. Notice that the derivative of this is going to be minus 32.6 plus 64. And that means that if I plug this in 0, I'm going to get the actual velocity that the stone was thrown. Okay? I can also find what is the moment where it's going to reach the maximum height, because this flat tangent line here is going to be reflected where the speed gets to be a 0. Okay? And so from this point on, I can reflect whatever the speed gets to be 0 with the maximum point in a parabola or this type of movement. Now, in general, the velocity of the stone is going to be the derivative of the position of the function, and the acceleration is the derivative of this. So as you can see, we have always constant deceleration. This is going to be always negative minus 32. So always is losing the speed. When the stone reaches the highest point, the velocity is 0, as I mentioned here. And to determine the velocity that the stone strikes the river, we need to figure out first when it reaches the river. So we need to find out who is the t for which the height is 0. So you can get s to be equal 0, find the time, and then after that we can plug in this speed function to find out when that happens. Okay. So let's actually go ahead and check when will that happen. So f is minus 16 t squared plus 64 plus 96. We're trying to find out when this becomes 0, reflecting this point. And notice that I can factor this minus 16 from here. And I'm going to get t squared minus in 4t. And then minus, so if I divide 96 by 16, I'm going to get a 6. Now at this point, I can factor this polynomial out to numbers such that the multiplication is minus 6 and the sum is minus 4. So we can have, we don't really have one that goes with those conditions, because numbers that multiplies gives you 6. You have 3 and 2 and 6 and 1, right? And there's no iteration of that so that you can get a minus 4 in here. So what we can do instead is do a quadratic equation. So if we find out this, we can say, well, t should be 4 plus or minus 16 minus 4, a is 1, and c is minus 6 over 2. So that gives me 4 plus or minus 16, and this is going to be plus 24. This is 4 plus or minus 4 by 10, which is 40. This 40 over here, over 2. And then this is going to be 4 plus 2 squared root of 10 over 2. And that's going to give me 2 times. T1 equals 2 plus square root of 10, or T2, 2 minus square root of 10. Remember that I'm simplifying 1, 2, and 1, 2 with this one. Now this is clearly a positive number, but very likely because 10 is a number larger than 9. So a square root of 9 is 3. Okay? So this is a number larger than 3. So that means that this is going to be a negative number. So this negative number is not going to work out. That can't be a time. Okay? So now if I calculate square root of 10, I find out I can find out what that is, and it's 5.16 more or less. And so at this point we're going to reach when t is equal 0. Okay? So the next step will be, okay, so I found that this is 0. That implies that t is equals 516. And so the next thing that I do to determine the velocity when it strikes the river is to plug in that b of 516, or minus 32, 516 plus 64. Okay? So this type of application is always about regularly finding a time, or finding a certain speed, or finding a certain acceleration. Now, let's discuss a couple more of possible applications. We have the economics and business applications. So in economics, we can have information about costs and fixed costs and variable costs. So imagine a company that manufactures large quantities of a product, such as mousetraps, DVD players, or snowboards. So we have associated to the manufacturing process a cost function C of X that gives the cost of manufacturing X items of the product. A simple cost function might have the form y equals C of X equals 500, which is the fixed cost, plus 0.1 X as the variable cost. Now, the fixed cost is independent of the number of items produced, and the per unit cost, which is the variable cost here, is giving you 0.10 cents per item produced. So the cost of producing 1,000 items is going to be 600, because this is going to give me 100, and then plus 500 more, you get the 600. Okay. Now, if we have that function, we can also calculate how this is going to look, and how the average per item is going to look. And so we have this cost, and we divide by X. That means that the function C of X over X is the average cost per item. Now in here we can see that this function of cost is a line, but now when we divide by X, it becomes a different function. It becomes a function like the 1 over X function, with asymptote at 0 and going towards 0 at the end. And so what that means is that the average cost is going to decrease once the number of items produced is increasing. So there's going to be a certain point where we're going to reach that the average cost is gonna lower a lot after a certain number of production, and that's the production that most products want to reach. Whenever the average cost of producing is reduced to almost nothing. This is the optimal point to produce margins of winnings. Now, now that we have that idea, we can talk about the average and marginal cost. Since you remember the average is a step from the notion of the derivative, then if we have the cost function C and then the average cost function, let's call it C var, then the marginal cost, the derivative, is the approximate cost to produce one additional item after producing X items. Okay, so this is very similar to the notion of the average velocity, then instantaneous velocity. Then we can translate that to economics and say, okay, so we have the cost, average cost, and then we jump to marginal cost when we get to the limit. So in the example of producing X item, where we have the cost given by the function minus 0.02 x squared plus 50x plus 100, then we can find out who the average and marginal cost functions are. And for the average, the only thing that we're going to do is divide by X, which is the amount of items. And to find the marginal cost function, the only thing that we need to do is calculate the derivative. So let's actually do that really quick. So we have C of X is minus 0.02 x squared plus 50x plus 100. And now the average cost is going to be this over X, which means minus 0.02 x plus 50 plus 100 over X. Okay, and now the marginal cost is going to be the derivative function of the cost, and it's just minus 0.04 x plus 50. Okay. Now then we can determine the average marginal cost for the first 100 items and make that interpretation. So in that is only plugging in here what is C of 100 and what is C prime of 100. Okay, so that's the general idea of this. And so if we calculate all this, we're going to get that the average cost of that is going to be $49 per item for the average cost. And for the marginal cost, using the same formula, we're going to get that we get $46 per item. So this result means that the average cost of producing the first 100 items is $49. But the cost of producing one additional item, which is the marginal cost, is approximately $46. Therefore, producing one more item is less expensive than the average cost of producing the first 100 items. Now, with this idea of marginal cost and average cost, then the economists apply the term of elasticity to prices, income or capital or labor, and other variables in system with inputs and outputs. The elasticity is going to describe how changes in the input are going to affect the changes in the output, which is especially good like for functions like the marginal cost of something or the cost of something. Since elasticity is involving change, then also is going to involve some derivatives. So the definition of the elasticity for functions, for example, if the demand for a product varies with the price, then with the function d equals f of p, then the price elasticity of the demand is E of p is equals the derivative of the demand with respect to the product times the product divided the demand. Okay. So, and this is just an example of calculating elasticity for a system where we're thinking demand in terms of price, which is where it's usually applied. But we can come up with different examples for the notion of elasticity. Okay, so this is part 1 of section 3.6. In part 2, we're going to be showing some examples of doing problems with this.